I presume.
Okay.
Okay. All right. Can everyone hear us? Okay. Let me.
Okay. Are we live, Mark?
Yes, we should be. Let me just like tag general to say we're starting now.
Okay.
All right. I see a few people. Hello, everyone. Can everyone hear us? Okay. I think they can. Yeah. Let me just double check.
Oh yeah, I see people commenting. Yeah.
I think I've. Oh yeah, I see Arun. Wonderful. Okay. Okay. Yes, perfect, Mr. Shahir. Thank you for confirming. All right, Phil. Hello, hello. All right. So I guess like welcome everyone. This is a very special episode because it's actually our 50th GPU mode lecture. So thank you so much everyone for humoring me for so long. Like really, this group started as a way for me to learn CUDA, and it turned into like honestly like my single favorite part of the internet. I'm hooked. I spend like about like 3 to 4 hours on the server every day. It's like ridiculous, but like that's my life now. So thank you for all being a part of it. So really, because it's a 50th lecture, I figured we needed a very special guest. So I'm super thrilled to have like Umar Jamil here talking to us about his journey learning CUDA, Triton, flash attention, and pretty much everything. But before the camera started rolling, Umar and I were talking for a bit. Like basically, first thing is people don't believe him that he started like performance work in 2022. But like you can go check the timestamp on a lot of his content. Also, like I really want to make sure to plug two different projects Umar does that I really like. Like one is, of course, his YouTube channel that has like some of the highest quality performance content on the internet. And the second is his Discord, where he's been doing this very popular 100 Days of CUDA challenge. So generally, just like a phenomenal person to learn from. And so yeah, without further ado, Umar, please take it from here.
Thank you, Mark. Thank you, Mark, for the introduction. So this talk is about CUDA, Triton, and flash attention. But in this talk, I will not be actually teaching you CUDA, Triton, and flash attention because I already made a 7.5 hours video on this topic. I will actually be exploring my learning journey in learning CUDA, Triton, and flash attention. Because the question I get asked the most is, how do I learn CUDA? How do I learn machine learning in general, etc.? So my machine learning journey actually started pretty recently, honestly. I coded my first neural network, I think, at the end of 2022. Yeah, it was November or December 2022. It was an image capturing neural network that I did for like my university project. And I remember during that time, we saw like a stable diffusion being released, and I started playing with it, and I started fine-tuning it, like using a technique called the textual inversion. I think it was also December 2022. And the logo of my YouTube channel is actually one of my first attempts at fine-tuning stable diffusion in generating pictures of me. What happened is that I got so fascinated that I quit my job and I said, I don't want to just use it. I want to fully learn it. And it took me nearly a year, like, to master stable diffusion and to going like from not knowing anything about PyTorch or neural networks in general to coding diffusion, stable diffusion from scratch on my YouTube channel. So people always kind of ask me like what was my journey, and it was exactly this year. That's how I changed my life. So usually whenever there is a big change in my life, it always starts with I quit my job, I go full monk mode, and I do something with new with my life. Anyway, in this talk, so we will be exploring like my own learning journey in CUDA, Triton, and flash attention, because my YouTube channel is not about performance in general. It's mostly about machine learning, and actually I teach about the things I learned along the my timeline of learning. So let's start our speech with a little ancient wisdom. So I think most of you are familiar with this ancient wisdom, which is give a man a fish and you feed him for a day, teach a man to fish and you feed him for a lifetime. I think this ancient wisdom worked for many centuries, but the goal of this talk is actually to challenge this wisdom, because I don't believe it works anymore. Because actually in our education system, so in school, in university, in college, whatever, they actually teach us how to fish. The problem is by the time we finish our studies, we are not close to the ocean anymore, but we end up in a jungle. And in a jungle, you cannot feed yourself by fishing. So how do you survive in a jungle when you cannot fish? Of course, you need to learn new skills. Probably you need to do hunting. Probably you need to do some gathering, or I don't know, recognizing poisonous stuff from non-poisonous stuff, etc. I believe that a modern version of this ancient wisdom should go along the following lines, which is give a man a fish and you feed him for a day, teach a man to learn new skills, and he will build a fishing boat to feed the entire village. Because once you teach a person how to acquire new skills, there is no limit to what this person will be able to do with his life. So this man who wants to feed himself will not just fish, he will build a fishing boat, he will build a rocket if necessary to feed himself. And that's why I believe that putting an emphasis on how we learn and what we are learning and our own learning journeys, especially with all these new technologies and tools we have right now, it's very important. So that's why I wanted this talk to be like a self-reflection moment. First of all, for myself, because I am learning constantly new things. And also I think for everyone following GPU mode, which is actually a learning community. Like we are here to learn about new technologies. All right, let's start with a little introduction for people who don't know CUDA, Flash Attention, and Triton. I will not go into the technical details. I don't believe this is the right talk for this, so I will keep it very generic, very high level, so we only explore the journey itself. So Flash Attention is an optimized implementation of the attention mechanism that is used in transformer models. So we have these transformer models, and the transformer models have this particular algorithm called the attention mechanism, which is, in the case of language models, allows you to like contextualize the text so that each token is not only kind of representing information about itself independently, but it captures information also about the context in which it appears. And if you think about the transformer is a neural network. A neural network is nothing more than a computation graph. A computation graph is a series of operations that take an input and transform into an output. When you use a model, you are transforming an input tensor, which is kind of a big matrix, a multidimensional matrix, into an output tensor. And when you're training a model, you want to convert this input tensor through a series of operations into a scalar called the loss. The attention mechanism is a series of operations. So when you convert it into a computation graph, it becomes one operation after another. The problem is each of these operations, especially in PyTorch, is through its dispatch system is converted into a kernel that runs on the underlying device upon which this tensor is stored. If you are using GPUs or NVIDIA GPUs, it is probably a CUDA kernel. The problem with the GPUs is that they are super fast at computing operations, but they are not so fast at moving stuff around. Why? Because GPUs have this memory hierarchy in which you have like this big memory called the DRAM, or also called the HBM, which is like the 80 gigabyte of the H100. And then you have this smaller memory, which is called the shared memory, and it's more closer to the cores that actually execute the operations. Now, the difference in size between the DRAM and the SRAM is huge. So what happens is every time you run an operation, a kernel, what happens is that this kernel will copy your tensor from the DRAM to the SRAM, so a slice of this tensor, so a part of this tensor, because you want to compute all the operations in this data in parallel. So there are multiple slices of this data. And if you think about matrix multiplication, for example, you know that the output of a matrix multiplication is just a series of dot products that you can compute in parallel. So you can think of each of these cores computing one output element of your matrix multiplication. So every time you have an operation in this computation graph, you're copying stuff from the DRAM to the SRAM, running operations on it, and then saving the result back to the HBM. The problem with the computation graph that has many operations is that every time you are going to the next operation needs to reuse the result of the previous operation. So you are, in the first operation, you copy the stuff from the DRAM to the SRAM, then you do some stuff with it, like addition, multiplication, or whatever, and then you save back to the HBM. Then the next operation needs to, again, copy from the DRAM, copy to the SRAM, do some operations, then save back to the DRAM. This copying of information actually makes the whole process slow because we are not fully exploiting the GPU while we are copying stuff around. So the first technique that is used is called kernel fusion, in which you do multiple operations on the data in one step instead of like saving intermediate results back and forth to the DRAM. And this is one of the first things that the flash attention does, which is make it IO aware and through first of all through kernel fusion. So if you do like a PyTorch attention mechanism naively, you are doing a lot of operations, while the flash attention fuses them into one big algorithm that do all of these operations, trying to minimize the copying that you are doing. What is CUDA? CUDA is a software stack from NVIDIA that allows you to write GPU kernels that run on the NVIDIA GPUs. CUDA is not the only software stack. It depends on which GPU you are using. If you're using AMD, we are talking about ROCm. If you are using, I remember AWS also have their own like Neuron GPU, so they also have like their own software stack. I'm pretty sure Google have their own software stack for the TPUs and etc. etc. What is Triton? Now, the problem with CUDA is that, the problem with all of these software stacks like ROCm or CUDA or whatever, is that you need to write a kernel that is specialized for the underlying GPU upon which you write it. And it's a very specialized knowledge. And it's very difficult to find people who are actually expert in writing specialized kernels for that particular GPU that you're using. Moreover, there is a steeper learning curve because you need to also have kind of write these kernels in C or C++. So a lot of machine learning practitioners are not aware of, not familiar with C++ or C. They mostly code it with Python. So it's there is a big talent shortage in this area. So Triton is kind of one of the solutions to fill this gap in talent, but not only, is also to make a more standardized way to write kernels that are kind of GPU hardware independent. So Triton is a project from OpenAI that basically allows you to write GPU kernels in Python with a very specific syntax and with very specific blocks. That is then compiled into a kernel that can run on the underlying GPU hardware, which could be CUDA and ROCm right now. I believe there is also other implementations, but I am not kind of super familiar with them. Okay, now that we have seen a little bit of what are these technologies, let's go to how to learn them, because the only question I get every day from people is, okay, I would like to learn Triton, I would like to learn machine learning, I would like to learn language models, transformer. How do I start? I believe that before you embark on a journey to start something new, always ask yourself, why do I want to study it? Why do I want to study Triton? Because if the answer is it's hype, it's popular on Twitter, it's popular on LinkedIn, don't do that. In my case, I always follow practical problems, and my practical problems was the following. I am very passionate about learning about new architectures in deep learning architectures. So every day, there is some new attention pattern, or there is a non-transformer model, or there is a long context modeling architecture. And I think since 12 months or something, they always come with kernels. Before, I think there was really very low knowledge of around the GPU kernel, so they usually just came with a paper with the flop calculation, but no practical kernel to play with. I think since Mamba was released, everyone is releasing also kernels for these custom architectures. So the problem is, every time I try to study these architectures, I wanted to experiment with them, train them. And a lot of times the code maybe doesn't work, or maybe it's too slow, or maybe it's not optimized for the particular GPU you are running it on. And I had to give up because I couldn't understand the kernel, and I couldn't understand how to fix it, or how to debug it, or just to understand how it works. After giving up many times on how to new architectures that I wanted to learn, I said, okay, time to go to Triton's website. This is the easiest way I can jump into the CUDA train, which is to code in Python and have it converted automatically by this amazing stack, which is Triton, into a kernel that can run on the GPU. So I went to the Triton website. And if you go open the Triton website, there is, of course, you start with the introduction and you look at, okay, what is Triton? Because I don't know, right? I just heard about it from some other people, so let's deep it. And if you look at this page, unless you have like a little background in the GPU programming, you feel super lost because you will understand half of what are the terms that are presented here. Now, a little disclaimer. I actually was aware a little bit about GPU programming because I studied it when I was studying Mamba. I made a video about Mamba in like December 2023 or something like that. So I was kind of already aware of like what is kernel fusion or what is the parallel scan, etc. But I never went super deep into it. But anyways, for this talk, I will actually pretend that I had zero knowledge. So I think I can like how to say like represent the typical person who is trying to learn it for the first time. So I went to the Triton website and I kind of got lost. And okay, what do you do when you get lost? I think before was Googling stuff, right? This is what you do probably, I think, 2 years ago. Right now you have your best friend and your best friend is called the ChatGPT or Grok. I think in life, you can never get blocked right now. Like anytime you're blocked somewhere and you don't understand something, you can always prompt. And why you cannot ever be blocked? Because you can just keep prompting until you're unlocked. Which doesn't mean that the GPT or through Grok or I don't know, Mistral or whatever you're using will give you the right answer, but they will for sure put you in the right direction. Because they can access the web, they can do deep research, they can do thinking, they can kind of also have the knowledge that is encoded in the training process. So they can at least tell you what is the background knowledge that you need to understand what you're trying to learn. And this is exactly what I did. So every time I got stuck in this journey, I always went to GPT. I like GPT, and I kept prompting until it unlocked me. And I believe most people like asking for roadmaps. I don't even understand why you need a roadmap, because you can build your own roadmap just by prompting. Keep prompting. Like you can ask it. I know a little bit of PyTorch. I know a little bit of, I don't know, TensorFlow. I know a little bit of NumPy. Build a roadmap for me specifically based on what is my knowledge. And it will actually build at least a starting point for what is a roadmap. And then you can just follow it by trial and error. You will figure out what is a better roadmap. Anyway, this is what I did, and this is what I recommend to do. Okay, suppose now that you know, at least you know what is Triton, so you can distinguish what is CUDA, what is Triton, what is flash attention. Okay, suppose that you don't even care about flash attention for now, you're just trying to learn Triton, right? What is the second thing that you need to do? Get your hands dirty, like start. There is very nice tutorials on the Triton website. Just do them. You don't learn by studying things. You learn, of course, sure, by studying things, but mostly by doing. So I, of course, also went to the Triton tutorials page, and I saw these amazing tutorials, which are also kind of categorized by difficulty level. So the first vector addition is the first thing that you do when you want to learn CUDA, and it's also the first thing that you do when you want to learn Triton. And when I was on the Triton tutorial website, my eyes got kind of illuminated by this fused attention tutorial. Because I said, wow, I never thought about learning about flash attention, because I can use it. I know it works. It's super fast. Okay. But I never thought about going deeper in flash attention. And I have here a tutorial that is coding flash attention in what? I think 300-400 lines of code. In pure Python, I have no excuses not to learn it. Now, I choose it also as a goal or a dream in my Triton learning journey. And I believe you should also have always a goal when you learn things. So as I said beginning of my talk, I don't know if this part will be cut or if it, I don't know if it was already being recorded, but as I said beginning of my talk, when I started my machine learning journey was mostly when I started using Stable Diffusion. And I realized that I could not just accept using Stable Diffusion. I wanted to learn it, and I wanted to code it, and I wanted to fully understand it. And I spent the next year trying to build up all the necessary knowledge to arrive to be able to understand fully Stable Diffusion. I still don't fully understand it because I lack a lot of knowledge. Like for example, if you ask me anything about stochastic differential equations, I have like zero knowledge on that. But still, I was satisfied when I reached my goal. And that's what I did also here. So I wanted to learn Triton, but I don't want to just learn Triton. I want to learn Triton to be able to have enough knowledge for me to understand the fused attention tutorial on the Triton website. Having an objective is super, super, super important. First of all, you use them to measure yourself against something that you can see, that you can, something that is measurable and that you can compare with respect to every day. So no matter what resources you are learning, no matter what articles you're reading or books you're reading, at the end of the day, you should ask yourself, am I getting closer to my goal, or am I just wandering around and getting lost? Because if you have a goal, measurable one, like this one, you will never get lost in your journey. Secondly, having like intermediate goals also gives you like a sense of satisfaction. Now, the way I like to learn things is I like to go like hardcore mode, which is I try to not watch the tutorials made by others, and this is also how I like kind of make videos on my YouTube channel. So, for example, to make my video about the attention mechanism, I didn't watch other videos about the attention mechanism. I read a few blogs for sure. First of all, because I don't want to get influenced in my journey, in my learning journey, and secondly, because I want to challenge myself. This is we are going a little off topic, but I strongly believe that life is just a series of challenges that you need to kind of overcome to prove to yourself that you can do it, so that later you can do even harder things. So that's why I like to challenge myself. So having a goal, having an objective is important, and you should also define what are the rules of this objective. Am I allowed to kind of only read papers, or should I also use any material that is available online? Depending on the difficulty of the challenge that you choose, you will improve your confidence. Because if you do hard things, it will improve your confidence. You will not only learn, but then later you will be less scared of tackling even harder challenges in life. Okay, now we have defined what is our goal. We want to learn Triton, but we don't want to just learn Triton. We want to learn Triton enough to understand that particular tutorial from the flash attention tutorial. And as like a side quest, we also want to learn flash attention. So, okay, now we need to start delivering. So I went to the first tutorial, which is vector addition. And vector addition is something super basic, but if you have never done like GPU programming, it's also hard because you don't understand half of the things here. For example, if you look at this addition kernel, if you write it in pure PyTorch, you will probably have two tensor as input, but here we have two pointers to tensor, two pointers to tensor. So why do we have pointers to tensors? We have them because you need to learn how tensors are stored in the memory and how GPUs access these tensors. We also have this thing called block size, and you may not be aware why do we do the calculation block by block. Why not just the entire thing on the GPU, one core at a time? What is this PID, for example? So a lot of people like going through this kernel. I'm pretty sure they will have the same questions that I also had at the beginning when I started doing these tutorials. So what I said before is, okay, I'm blocked somewhere, right? I don't fully understand it. The first thing that you should do is run it, at least make it runnable. So install Triton, run it, and when it runs, you have two options. Either you learn it by running it and debugging it, and you can debug Triton kernels by using the interpreter. So there is an option in Triton that allows you to kind of run the kernel using the NumPy backend. So using the NumPy backend, it is kind of simulated. So each block is executed one after another. So it's not really parallel, but helps you kind of understand what happens block by block, what happens under each operation block by block. I think if you go to the Triton documentation, it's like here, debugging Triton. So they teach you how to use the interpreter here. The other way is, okay, we are not fully understanding it because we lack some knowledge. And I realized that by just prompting ChatGPT that I lack some knowledge. So I went back to GPT and I asked, okay, how to fill this knowledge? And all the resources were pointing to this book called the PMPP. programming massively parallel processors. Now, we are trying to do the vector addition tutorial, and we found an obstacle, and we found resources on how to kind of overcome this obstacle. Should we go to this new resource and fully immerse ourselves in this new resource? No. You should always remember where you are and why you are going to a new resource. You are trying to do the vector addition tutorial on Triton website, and you are blocked because you have a little knowledge, a little gap in your knowledge. So we go to the PMPP book, but we don't just start grinding the PMPP book like blindly. We just learn enough for us to understand the things that are relevant to the vector addition only. Every time you do a change in your resource, always make sure where you are, and you need to come back there because your goal is always the same. You are doing Triton to learn flash attention. So you should always try to stay on your path unless you really want to change your goal. And this is what I did. I went to PMPP. I learned the first 2 chapters, I think, enough for you to understand vector addition and to give you a little intuition on all the concepts that you need to at least understand fully that tutorial. And then also all the other tutorials, like if you go to, for example, fused softmax, you need to understand how the softmax is computed, what is the safe softmax. Of course, you may not know that. So you go to another tutorial, or you go to another website, or you go to another blog. Always learn enough to go back to the tutorial, because you do it and then you move on to the next one. Then you go to matrix multiplication, and you will probably not understand why we are doing it the tiling process. Maybe you don't know what is memory coalescing, so you go to the PMPP book, learn it, and go back to and finish your you finish your tutorial. The other tutorials are also kind of in increasing level of difficulty. So I think there is no backpropagation until layer normalization. So layer normalization is the first tutorial that has also the backward pass that you need to compute, and for that you need to kind of review what is the gradient, how to compute the gradients, the Jacobians, etc. Anyway, I did all the tutorials until layer normalization, and then I finally was ready to fight the final boss, which is flash attention. Flash attention, if you look at the tutorial on the Triton website, it starts by introducing, okay, what is the attention? And they refer you to the paper of the flash attention. And this is also what I did. I went to the paper and I started reading the paper. When reading the paper, also you will encounter a lot of things that you may not be familiar with, and like many actually, and especially if it's a paper, very technical paper, and from on something that you're not how to say, using GPU programming every day. So there is a lot of terms that are specific to the GPU programming community and this field. So I also there was a lot of things that I didn't understand on the paper. So what I did before, and what I have been telling you to do before, is, okay, every time you encounter an obstacle, prompt GPT and then overcome the obstacle and go back. However, for paper, I do something slightly different. So instead of going down rabbit holes randomly and trying to cover the knowledge gap that you have, I suggest the following, which is read the entire paper, top to bottom. Why? Even if you understand only 1% of it. Why? Because first of all, when you're reading a paper, the first thing that you want to make sure is you want to have an overview of what are we talking about, and you want to kind of annotate all the things that you don't understand before jumping to learn about them. And I know that it is very uncomfortable to read a paper that you don't fully understand, because you're constantly reminded of all the things that you don't understand. And it makes you really feel uncomfortable, especially if you're trying to enter the field. Like when I was trying to enter machine learning and I read the paper, I said, wow, I'm so behind. I will never make it. It's going to take me 25 years. So it's super uncomfortable only for this reason. But you need to force yourself to do it. So just read it top to bottom. And there is no other way to understand fully what are the top things that you need to overcome to kind of fill in your knowledge. What are the things that you can kind of ignore because maybe are not so relevant for your journey? And what are the things that you already know? And plus, your brain is actually very smart at connecting dots, even on things that you are not fully familiar with, that you don't fully know. So sometimes, like if you learn about something, and this it's a totally relevant new topic for you, your brain will always kind of sometimes find an interpretation of what you're reading, which may be wrong, but okay, it's always satisfies to kind of have an intuition by yourself. Another thing that I recommend doing is highlight, but don't highlight while reading. This is also something I used to do before. Highlight after reading, because this forces you to go through it again. Of course, not every paper you can do it like this, so it depends really on the level of depth that you want to reach. In this case, I was trying to master flash attention, so I had to read it multiple times before I could come up with a plan of how to tackle it. And the plan was the following, more or less, and this is more or less the kind of the things that I teach in my video. So I was already aware of what is the attention mechanism. I was already aware of what is the softmax, what is the problem with the softmax, how to compute it in a safe way, like you don't want the exponential to explode. And I was not aware what is the online softmax. I was a little bit aware of what is GPU programming, HBM, shared memory, tiling, etc., tensor shapes, but I was not like super confident on the more advanced topics. And then, of course, there is the thing about backpropagation. So all this roadmap was built by going top down to the paper and highlighting the things that I found difficult for me to understand. And then I prompt GPT. I said, okay, I don't understand this term. Where does it come from? What is this field? Is it like, should I learn it, I don't know, from a math book? Should I learn it from the PyTorch website? Should I learn it from... Give me some resources to learn it. So I could build this roadmap just by prompting GPT and by reading the paper. Okay, now that we have a plan, we need to fight all these bosses. So the first boss was softmax. So if you go to the flash attention paper, they tell you about what is the problem of the softmax if you compute the attention block by block, because you need to compute this normalization factor. And in order to compute the normalization factor when you're computing the attention block by block is to do it in an online way. And actually Triton is very good because he already actually give you the two resources that are relevant for this, which is the citation number 60 and 66 from this paper, which is the following two paper. The first paper that is relevant for this topic is the self-attention does not need O(n) squared memory. This paper basically teaches about the lazy softmax, so the fact that you can compute the normalization factor, you can apply the normalization factor of the softmax while doing the multiplication for the V when you do the attention mechanism. So softmax of the query multiplied by the transpose of the keys, and then you multiply by V. So during this multiplication by V, you can actually do the normalization factor for the softmax. And the other paper is the online normalizer calculation for softmax. This is the paper where I actually learned how the online softmax works. And this is actually how it is done in flash attention. So if you read this paper, Online Normalizer Calculation for Softmax, it is a very interesting paper because it is simple, super simple to follow, first of all. There is an algorithm on how to, they work step by step, like they show you what is the softmax, what is the problem with the softmax, I mean, if you want to compute it online way. And they do a first iteration, they do another iteration. So it's very nice to follow. Now, when you read a paper like this, reading is not enough. You need to have some form of active learning. Active learning means that you need to use your hands and annotate stuff and take notes and try algorithms by hand. The first thing I did, and I do usually when I want to master a paper like this, is to, if there is an algorithm, very simple one, I just screenshot it and ask GPT to code it because I want to run it. I want to, like, for example, this one is a super simple algorithm that you can just have a random vector and run it on a random vector. So code it by yourself, or you ask GPT, or whatever you like. The second thing I do is test it on a paper, but this is optional. This is up to you. I mean, if you want to code it and then test it on the debugger, it's all up to you. What is very important is that if you are trying to learn an algorithm like this one, that is like an iterative algorithm, and if there is a proof, read the proof for sure, but don't believe that reading the proof and reading the proof is enough, because once you read the proof on a piece of paper, your brain probably thinks that it understood it because things make sense while reading, right? the problem is they only make sense in the kind of bigger picture. I mean, only the big pictures make sense, because your brain doesn't have enough time to concentrate on the small details. So how to force your brain to concentrate on the small details? The first step you can do is to rewrite the proof by yourself on a piece of paper by copying the proof from the paper, the original article. This will force your brain to engage in a thought process every time you make a stroke with your hand. So every time you're making an equal sign, your brain is thinking, okay, why am I making an equal sign? Why is not like a greater than? Why not less than? So you are questioning yourself each step that you're doing. And the second thing is, if you want an even deeper understanding, just like check the hypothesis and try to come up with a proof by yourself. Probably you will come up with a different proof because not all the steps will be the same, and that's totally fine. That's where you learn. Like when you can recreate something differently, that's when you have actually understood it. So this is like the steps that I took to learn this online softmax. Now, actually, when I was learning this paper, I didn't fully understand how it connects to flash attention, because here they do it scalar way. In the flash attention paper, they use the vectorized form of this, and plus they combine the two results. So okay, not in the flash attention 1, I think in the flash attention 2, they do also the normalization part at the end. So when they do the multiplication by V. So actually, okay, you can't just like read about the online softmax and automatically fully understand how it's used in the flash attention paper. If you do, wonderful. If you don't, then you're just like me. So what should you do in this case? Like, should you keep trying to read the paper online softmax until you figure out how it's used in flash attention? What I do usually in these cases is go back and forth. So I go to the flash attention paper, try to understand how it's used. Then if I don't fully understand it, I go back to the online softmax, because every time you go back and forth, you are reinforcing the learning that you had from the other content. So when you go back to the online softmax from the flash attention paper, you are reinforcing your learning of the flash attention by having it kind of trying to make it work with whatever you're learning from the online softmax paper. Let me cough a little bit. I will mute my... Okay. All right. So in this case, what I did, and this is also something I do like when I'm trying to learn a new architecture, when I read a new architecture paper, I don't actually fully understand all of it just by reading the paper, unless I'm already familiar with the concepts behind it. So if there is like a new attention pattern, probably I fully understand it by reading the paper. But if it's totally something new, like a new recurrent neural network or something that is using a totally different form of attention, then probably I don't fully understand it. In this case, what I do is combine it with the code. So I go back and forth between the code and the paper. This is the only way to do it. Most of the time, these codes are actually quite cryptic, and because they are written by researchers and not really good engineers. So it's really difficult to follow them unless you have the paper also on the other side. So you need to combine these two things. And this is also what I did for the flash attention and online normalizer. Okay, the second boss that we need to fight, and this very ugly drawing is from my video. So in the video, basically, I don't make the beautiful slides anymore because I don't want to spend too much making beautiful slides. I want to spend time making useful content for people. And I try to draw all of these things by hand. This also actually helps me to become better at whatever I'm doing. So the second boss here is a block matrix multiplication, which is super simple. So basically, when you do a matrix multiplication, is you know you can compute the output of the matrix multiplication by doing a dot product between one row of the first matrix with one column of the second matrix. However, you can also divide these original matrices into blocks of elements. What does it mean? That if the original matrix is 8 by 4, you can group elements like 4 by 2 elements, and the first top left group of 4 by 2 elements, you call it A11, and the second block you call it A12, etc. And you do the same with the second matrix, and you can choose the arrangement as you like. You don't have to use the same number of elements as a block. And if you do like the matrix multiplication between blocks, so you treat these blocks just like scalars, so the output matrix will have the same elements as the original matrix, just in terms of blocks. So this element here will be a block of elements that results from the dot product of this block here, this row of blocks, with this column of blocks. This is something you can always do with matrix multiplication, as long as the shapes are compatible. And this is very important in flash attention, because we do the computation of the attention block by block. So we take a block of queries, a block of keys, and the corresponding block of values, and we do this multiplication block by block, while fixing the normalization factor for each of these blocks as we move to the keys and values. Another boss that you may need to fight is this tensor shapes and strides. So I am going very briefly on all of these topics, because I already described them fully in my video. So this is mostly to teach you like what are all the different topics that I touch. So another thing that you should be aware of is the tensor shapes and how they are kind of mapped in the memory. So tensors are multidimensional arrays you can think of, or multidimensional matrices, like n-dimensional matrices. And the thing is how to represent them in memory. Now, if you look at a vector, a simple vector, 1D vector, this vector is made up of 7 elements, and these elements are present in the memory one after another in contiguous addresses. So the first element is at the address 100, the second element is at address number 102, etc., if each element is of 2 bytes. And each tensor has a property called the stride. The stride tells you how many elements you need to skip in order to go from one element of one dimension to the next element of the same dimension. In this case, the tensor is only one-dimensional, so in order to go from one element to the other, you just need to skip one element. So 1, 2, 3, 4, etc. If you have a 2D matrix, then you have the following stride. So imagine the shape of this matrix is 2 by 3, so 2 row by 3 columns. The stride in this case would be 3, 1, because in order to go from one row to the next, you need to skip 3 elements. And how is the stride computed? It's just the product of all the shapes that come after the dimension of the stride. So in this case, this 3 comes by 3 multiplied by 1. And this 1 is because in the last dimension, to go from one element to the next is always 1. The advantage of keeping track of the stride is actually that it allows you to reshape or view this matrix in different shapes without having to rearrange the physical view, so the elements in the memory. So for example, if you want to reshape this matrix from 2, 3 to 3, 2, so you want it to become 3 rows by 2 columns, you just need to change the shape and recompute the stride. So the stride is always recomputed in the same way. So I take the shape of all the successive elements of the shape and I multiply them together. In this case, we have only one element after this stride, so we only have 2. So if you want to verify this, it's super easy. So in this case, the stride is saying that in the physical view of the memory, in order to go from one row to the other, we just need to skip 2 elements, which is true, because if you go 1, 2, if you are at 1, you just skip 2, and you go to 3, which is exactly the element of the next row. Another advantage of keeping the stride is that you can transpose for free, because you don't need to rearrange the physical view of the tensor. So how to transpose a tensor or multidimensional tensor? You just swap the elements of the stride of the 2 dimensions that you are trying to transpose. However, when you transpose a tensor, the tensor loses its contiguous property. The contiguous property basically means that if you want to reshape it again, then you have to kind of rearrange it in the physical memory. And this is also one of the reasons why in PyTorch you have 2 functions for viewing a tensor, which is one is a view and one is a reshape. The view is something that you can only do if the tensor has not been transposed before, so it's contiguous. Reshape always works because it will rearrange it in memory if necessary. But anyway, this knowledge of how tensors are arranged in the memory is super important, not only for flash attention, but also for all the other kernels that you will code, because the GPU will only be provided with a pointer to what is the starting point of the tensor in the memory, and then you have to compute all the other elements by yourself just by using the stride. The last boss that we need to fight is the backpropagation. And this is honestly the most difficult part if you are not aware of like a gradient calculation by hand. Because in the flash attention paper, of course, there is also the backward pass, and you need to compute the gradients. So how does backpropagation work? The way I teach it in my video is the following. So first of all, why do we need backpropagation, and what is gradients? So when we train a neural network, we have this computation graph, we take the input, we compute the output, we transform this output into a scalar called the loss, then we want to compute the gradient of the loss with respect to all the parameters of the model. How to do that? Well, PyTorch basically is just a person who goes to each operation in the graph, on the computation graph, and asks the following question. If I give you the gradient of the loss with respect to your output, can you give me the gradient of the loss with respect to your input? And the operator will say, yes, I can do that because I have chain rule. So in the case of matrix multiplication, what happens is the following. So imagine you are doing a matrix multiplication between an input matrix X and a weight matrix W. So the operation is X multiplied by W. And these are the shapes of the matrices. What PyTorch will do to the matmal operation, so what do I mean by this math multiplication operation? It is basically in PyTorch, all operations are kind of objects that derive from the class function class, and they provide the two operations. One is called the forward, one is called the backward. If you want an example of that, you just go to the Triton tutorial here in the fused attention, and I'm pretty sure there was one. So let me try the function, I think it's called. Oh, let's here. So every torch kind of operation is a class derived that from this class, which is the function class, which provides two functions. One is the forward and one is the backward. The forward takes the inputs and then computes the output, and the backward will take the gradient of the loss with respect to the output and compute the gradient of the loss with respect to all the inputs. In the case of matrix multiplication, we have two inputs. One is the activations and one is the weights, and we want to compute the gradient of the loss with respect to the activations and to the weights. How to do that? Well, the naive way would be to do it with chain rule. So if we have the gradient of the loss with respect to the output and we multiply it with the Jacobian, that is the Jacobian of the output with respect to the input in this case, so dy on dx, we can compute the gradient of the loss with respect to the input. However, this naive way is not computationally efficient because this Jacobian here would be too big to materialize in the memory. And moreover, it's actually sparse because if you think about matrix multiplication, the first row of the output matrix just depends on the first row of the first matrix in the matrix multiplication and all the columns of the second matrix. So it means that the gradient, the partial derivative of the first element of the first row of the output matrix will not depend on any other row of the first matrix, only on the first row. So this Jacobian will be mostly sparse. So it's not even worth it to materialize it. Usually, we can always come up with an implicit formula that does not involve the materialization of the Jacobian. And in the case of matrix multiplication, it's a very simple formula that you can kind of memorize. And the mnemonic rule that is, okay, this is kind of very famous, is if you don't, you want to understand if it's the gradient of the loss with respect to the output multiplied by the transpose of the weights, or is it the transpose of the weights multiplied by the gradient of the loss with respect to the output? Well, it's the only configuration that makes the shape work out, because the gradient of the loss with respect to a particular parameter, so particular vector, which could be the W matrix or the X matrix, has always the shape of the matrix itself. So the gradient of the loss with respect to the output has the same shape as Y. The gradient of the loss with respect to X has the same shape as X, and etc. So the mnemonic rule is the only combination of transpose and multiplication that makes the shapes work out. Okay, so now we have also know what is the last boss, and these are all the things that I had to learn for learning flash attention. And why I learned flash attention, because I told you I was trying to learn Triton, and I wanted to have a specific goal that grounds my research only to the specific things that I need to learn flash attention. And why I chose flash attention? Because once I teach myself flash attention, it will improve kind of my confidence in tackling even more challenging stuff with CUDA or Triton later, because if I can prove myself that I can learn something that I always thought as being something super difficult, super complex, then I built enough confidence to go further. So I also recommend doing like this. Always choose a challenge, do it, and move on. Now, another question I get from people is, okay, what should I learn next? Because there is a lot of noise in the market, like everyone is doing CUDA, everyone is doing, I don't know, Triton, everyone is doing reinforcement learning recently, and now people are doing I don't know, generic agents, I don't know. So what should you learn next for your career? Honestly, I have no idea, but there are few rules I follow. So the first rule I follow is follow curiosity, not hype. Like as I said before, when I started doing my machine learning journey, which was really I started coding neural networks at the end of 2022. I ground myself to only learn the necessary things that takes me towards my goal, which is to fully understand stable diffusion. And I only did that. Of course, there are some like other intermediate, how to say, things that I learned along the way, but I didn't kind of master them fully because my only goal was to understand that. I wanted to reach that goal and then say, okay, what is my next goal? This is very similar, if you want to have like an analogy, to what Forrest Gump does. So he runs from the west coast to the east coast, and then he said, okay, what's next? And then he will find the next goal. In his case, he's probably run to the other way around, but in your case, you can choose something different. The second rule is focus on consistency, because it doesn't really matter how bad your start is. Eventually, with enough time, with enough consistency, with enough trial and error, you will always fix any initial bias in your learning process. I also kind of I started learning, as I said, very late compared to like the other machine learning practitioners or machine learning researchers. But just by putting in more hours, more consistently, I could catch up fast. So I think you can do the same. Like it doesn't really matter which roadmap you're following. And honestly, like with the learning tools that we have now, you can learn very, 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 very fast. So if in school something took you like 6 months to learn, right now you can learn it in 1 month. Why? Because if it doesn't happen, it's you are not using the tools correctly. I used to spend a lot of time trying to understand things. For example, imagine in a derivation, for example, you cannot understand a step. Before, what I used to do is, okay, try to search on Stack Overflow, Stack Exchange, Math Stack Exchange, Google, keep searching until I find something that helps me unlock on that step that I cannot understand. Right now, I just prompt and it unlocks me. Now, this doesn't mean that the model will give you the right answer, but it will kind of at least put you in the right direction. And then just by prompting, you can refine this direction further and further and further. So the language models actually, what they save you is in the Googling time, that you don't have to kind of spend 1 day Googling things just to find what is the direction. Right now, you can immediately find the direction and then just follow it to unlock yourself. So I strongly believe that right now you can learn 10 times faster than like a few years ago, the same things. So if it's not happening for you, I'm probably sure that you are not using the tools correctly. Another thing that I do is to avoid the noise. And there is really a lot of noise in the market right now, like a lot of noise. So every day I see people going from one topic to the other, following just the hype. And this is wrong, because you should have a journey that is built specifically for yourself with the tools that are available right now. And you just need to commit to it. I know at the beginning it's difficult to commit to something that is you are not aware of. And it's fine at the beginning of your learning journey to kind of explore different things, but you should have a long-term goal for your learning. So I want to master language models. That should be your long-term goal. Then you can have intermediate steps that are relevant to this journey. You can also do some other cool projects in the weekend. That's totally fine. But you should always measure yourself against your long-term goal. Once you reach it, then you build another long-term goal. And this is what I also did with the Triton. So I had a long-term goal, I reach it, and then I said, okay, what's next? Then I will choose what is my next goal. Honestly, right now I'm kind of on a break from Triton because right after publishing the video, I became a father, so I wanted to spend a little time with my daughter. So I hope the community will forgive me. But anyway, there is really a lot of noise on social media, and you need to avoid this noise. And now I call this thing the dual stream learning, just like the CUDA streams, which means that you have like one stream that is dedicated to the noise, which means that you read the papers that are being published around, but don't just jump into them. Don't just, okay, like now I drop CUDA and I jump into the reinforcement learning train. Then there is the diffusion language models the other day. So now let's jump into the diffusion model train. So read about them because it's relevant for you to know all these things that are coming from the literature, but doesn't mean that you just need to master them immediately. You can pivot, you can change idea later, even if you are halfway on your long-term goals, that's totally fine. But if you keep doing it constantly, I think you're doing something wrong. So have something like built on the long term. Also because mastery only comes from long-term commitment. Like you cannot master something just in a few days. Your brain needs time. This is something I learned by studying Chinese. So Chinese is a very complex language that even if you try, you cannot master in a short term because your brain just can't handle that much information. Like you try to memorize all the characters, you just if you try to memorize 100 per day, maybe you can, but you will probably forget most of them the next day. So it takes time, and also this happens with all the learning processes in any kind of field. Now there is one secret ingredient that I didn't talk about, honestly, in all this learning journey, and the secret ingredient is always the following. And I don't want to show it, but I want to expand it, and it's this one. So the secret ingredient, guys, it's always you. Why? You are the secret ingredient because you need to, first of all, convince yourself that you can learn the things that you're trying to learn. You need to convince yourself that you will be able to do the things that you want to be able to do. And you do that by building confidence. And confidence comes from doing hard things. So if you are just watching tutorials online, passively trying to understand things, you are not doing something hard. You are just building enough knowledge to unlock you on something. But then you need to deliver. To deliver means you need to push yourself further. And honestly, I have been giving kind of the wrong message with my YouTube channel, and that's why I started the Discord channel. I was teaching things, but I was not telling people to move further from the teaching. So people were following tutorials, they were learning, but then they just stopped at the tutorial. Honestly, this is not enough nowadays because GPT can generate better code than me. So GPT can follow tutorials. GPT can recreate the blogs that you can find online or the GitHub repository that you can find around. What GPT cannot do is the hard things that take effort, that take active learning, that push yourself, your learning to the next step. To do that, I highly recommend that you push yourself by trying to improve the things that you watch, that you learn around. And the second thing is, I strongly recommend actually to jump into the leaderboard at GPU mode, even if you don't fully feel confident about the kernels that you're building. Why? Because the only failure is not being in the bottom of the leaderboard. The only failure is not showing up. So if you just show up in the leaderboard, that's just proof that you challenge yourself to try to do better than what you read on the book or what you read on the tutorial and what you read on, I don't know, some YouTube video. So build confidence. That's the only thing that will take you far. Okay, I think I am done. Thank you for listening.
Okay, this is awesome. Thank you, Umar. I think chat is pretty fired up. So folks, so folks, Umar said he's happy to answer any questions y'all might have. But like in the meantime, Umar, I've been writing down. I think I have like 10 questions for you. So if people don't ask, I'm just gonna keep going through them. So in the very beginning, you mentioned something that stood out to me, which is you quit your job to sort of really like dive deep into learning stuff. I did the same thing after my first job at Microsoft, and many friends of mine thought it was insane. I'm also not sure myself, even in hindsight, if it was like a correct decision. So I'm sort of curious, is this advice that you give to people in general? Is it something you think is just like, yeah, like just curious to hear your thoughts?
Okay, so how things my life, I think I have had many challenges in my life, honestly. um, as I said before, I like to go full monk mode when I try to do things, which means I like to just concentrate on the things I want to achieve. For example, in 2020, I was in China. I was working. I was doing a business trip in China for an Italian company, and I met my wife. Now, I never thought about my life as I never thought about living outside of Italy or even starting to live in China, etc. So I met this amazing woman, and I wanted to date her, and I wanted to have a life with her, and I wanted to marry her. The problem is I was scared. I was scared because I didn't know how to build a life in China. I didn't speak Chinese. I didn't have a degree back then. I'm a bachelor dropout. So I just had a high school degree. So imagine me trying to compete with the Chinese people on a job without even a degree, which is super, super, super valued in China. Like they consider it the bare minimum that you need to have. And if I wanted to even have a visa to stay in China, I needed to have find a job that pays 4 times or 6 times the local salary. That's how you get the talent visa. So I didn't know anything, but I decided to quit my job. So I started networking with people. I started going around. I started learning Chinese. I started doing whatever it takes to be in China. And eventually did it because when you put yourself in trouble, I think you always find a way out of it. But if you never get yourself in trouble, you will never have the motivation. And in my case, I had a big motivation. I really wanted to spend my life with my wife, so it was really worth it for me to do whatever it was necessary to be with her. And eventually it worked out. In the case of my career change, I met my wife, and my wife was working in machine learning. That's how I met machine learning in the first place. Actually, I actually did, before even meeting my wife, I did one conference in the Silicon Valley about machine learning. That's when I went to San Francisco the first time, 2019. But I just was an observer in the machine learning. I never kind of engaged in it. So my wife said, okay, why don't you kind of get a degree in machine learning? At least you can get a stable, you don't have to struggle to find a job that pays 6 times the local salary just to get a visa for staying here. So that's why I joined a master degree. But honestly, I was not satisfied with what I was learning with the master degree because, as I said at the beginning of the talk, they teach you how to fish, but they don't teach you the relevant skills that are necessary for the job. So I was learning about pandas, about all these amazing libraries, but that's not where the word is. The word is already 10 steps ahead. So how can I catch up? I said, okay, I can either spend my life being an observer in this, or I can just chase it. Now, where I am lucky in this, I am lucky because I have a amazing family support. Like my wife said, if you want it, go for it. My in-law said, if you want it, go for it. Don't worry about providing. Don't worry, we are working here. You just do what is necessary for you to do. And that's why I quit my job, honestly, because I wanted to accelerate my rate of learning. Before, I was working as a manager. So in working as a manager in China means that you work actually a lot. China is not really the kind of places you think about when you talk about the work-life balance, right? So I was working really a lot, and I was putting, for the university, I was also putting 20 hours per week at least, but it was not enough. So if you want, you just need to believe in yourself, and that's why we are talking about confidence here, and then you just do it.
All right, so I think I heard like the TLDR for me there was really sort of create yourself this huge sense of urgency and find yourself a beautiful wife. So I think this is sort of like it's very good. It's very good timeless advice. I'm going to ask like one more question, and then I'll go to questions in chat. So a very common question I've been asked personally, where I just don't know how to answer it very well, is when people ask me for like a roadmap of how to study things. Like they go like, I know a bit of Python, like should I learn CUDA or Triton, or math? And I'm like, I don't know, like all of them. Generally, I don't know what the right order is for the most part, but certainly for me, it wasn't as structured. And so I'm sort of curious if you've sort of found a good question, a good answer to this question over the years.
So I'm a very practical person. I usually learn the tools that are necessary for me to do my job. Honestly, I'm not a master at CUDA. Like I never studied more CUDA that is necessary for me to learn flash attention. So I have a very basic knowledge of CUDA, honestly. So what I believe is set yourself like a problem that you want to solve from your own life, like I want to learn this for what reason? Do I want to just code like a transformer and recreate the transformer? Wonderful. Then you can just learn these things. And it's, don't worry about things being useful as long as they are useful for yourself, for learning. I know the biggest problem I think is always cut the noise. People will tell you, you need to know this because there is TileLang. Why don't you study TileLang? Spend 3 years learning it. Yes, you can do it, but is it relevant for you? Is it relevant for your journey?
So I guess one of the tricks I've used over the years, which I've had to break as of last year, has been like I only like read about projects or papers if they're more than 2 years old, because like I let time do the filtering. These days it's a bit tougher to do this, but like I would say for most of my career that was a heuristic I followed.
Yeah.
Okay, I guess I'll start going to questions. The first question I see is like really around like which GPU mode leaderboard this is. So just for context, folks, you can basically submit basically CUDA or Triton kernels within Discord directly. Go to the submissions channel on the GPU mode Discord and like basically pick a kernel and start competing on it. We're planning on releasing at least like 5 to 6 problem sets a year. So basically one competition every 2 months, and the next one is going to be on LLM inference perf. Okay, I see this other question from Dylan. So this is like really around like AI tools accelerating your learning. I guess you can see the question on chat, right?
Yeah.
I'll let you read it.
All right, so you mentioned that the AI tools should accelerate you. Any specific advice as to how to achieve it? Okay. I would say that right now, I think the biggest problem people have is should I use Cursor as a learning tool, or should I use Cursor to get jobs done? I think this is the same thing as if you should code your own AutoGrad, or you should code your own transformer, or you should code your own like a NumPy from scratch, or whatever people code from scratch. Go for it if you want a deeper understanding. So if you want, for example, a deep understanding about something, don't use Cursor. But if you want to get things done fast because you want to recreate, for example, DeepSeek R1, then go for it. If you want to have like a big project done. Now, what other tools I use? I mostly use a lot of prompting. Like I spend a lot of time just prompting things. Why? Because it unlocks me. So every day I'm doing something new, and I think every day you will probably in any job you go. I think right now it's not about how many APIs you memorized, is how many problems you can solve. And to be able to solve problems, I think you need to use the right tools. So just learn to use prompting the right way. I think Karpati did a video the other day. All the things had these uses, like all the possible ways to use a language model. I think more or less I would agree with whatever in the video is presented. So I mostly spend time like using I think language models, and I try multiple of them. Like sometimes I try the same prompt on Grok or the GPT. I try another one. Another thing I use a lot is every time I don't understand the derivation, I just take a screenshot of the derivation and ask GPT, hey, I cannot understand how to go from step number 5 to step number 6. Can you help me, please? That's it. This is and I use a lot of actually Cursor. I use a lot of Visual Studio Copilot. Why do I use it? Because it accelerates the I mean, before, for example, if you want to learn about something, you want to code something. Imagine you want to code LLM.c, like Karpati. There is a lot of code that is not necessary for you to learn things because it's just repetitive. That code, you can just ask Cursor to do it for you. And the other code that the specific code that like, I don't know, the AutoGrad system or something more relevant, that part you can code by yourself. So you can kind of choose when to use the specific tool, even inside of a single project, instead of doing it per project.
Yeah, like it reminds me of like studying chess. Like you can sort of use engines to understand like high level theory or which openings are worth investigating in, but like you probably don't want to use a chess engine to learn combinations because that's really a skill set you want to cultivate. Okay, so I see another question by Osama, putting it up.
Oh, how important was learning low-level skills in your learning journey, and do you think it is important for increasing programming maturity in general? Of course. I believe that it depends, again, on what is your goal. If you want to master something, you need a low-level understanding of that something. There is no other way. And if you want to master something, I strongly believe that you need to recreate things by yourself from zero, from scratch. I know that people will think, why not just it's useless because a cursor can do it very fast. But yeah, but it's useful for you to understand. That's the only way. You should always do things that are useful for you, not that are useful for the world. If they are also useful for the world, kudos.
All right, I see another question from Sna Surab.
I have only 1 hour or less to study per day. What do you recommend? I studied China. Oh, sorry, this one.
So yeah, so
Okay.
is it possible to learn advanced deep learning and GPU optimizers without access to a machine with GPU?
Of course, it is possible. So when I started training models, I didn't have a GPU. I just had Colab, for example, and that's also how people have been learning like kernels on the Discord channel. There is also now a new website called the Lit GPU. I think there is like a presentation about Lit GPU, and they kind of let you simulate also. In Triton, I think you can use the Triton interpreter without having a GPU. I think it will just work out of the box. It will be slow, but you can always try the Triton kernel on a small amount of data, and it will be decently fast.
Yeah, maybe to add to that, like even H100 GPUs aren't as expensive as they used to be. Like they're like around like $1.30 an hour for like a state-of-the-art GPU. And I'd recommend like there are websites, like there are websites like Vast AI that you can like also go to if you want like cheaper GPUs, but you'll probably pay in the ballpark of a few cents per hour.
Do you need to be good at math or programming for AI research? I think you need to be good at whatever is necessary for you to become whatever you want to be. So I think that in life, if you want to do something, just learn the relevant things if you really want it. Imagine I ask my wife, should I look beautiful for you to marry me? I don't know. She would say you need to be the best man in the world. So just be the best man in the world.
Yeah, at least like my grad school advisor, like a very wise person called Charles Elkin, often told me that like questions that are like, should I do X or Y? Often the right answer is both X and Y or neither. And I found that very helpful to sort of make decisions. Maybe you too will.
Yeah, but I think I think work go by step. There is no like AI researcher role. Like every researcher is different. Every researcher is doing different things. Start doing research. Start basic, and then improve upon that. Again, learn by objectives. Simple objective. You reach it. You build confidence. You move on to the next one, and then you keep doing like this.
Right. We have a question from M. Shahir, which is he's finishing his PhD in robotics. How much should he go in detail for deep learning? Should he go full in depth of CUDA or just use the models? Is it enough?
Again, depends on what you want to do with your life. Yeah, I think you can. I like to go deep because this is something I want to do, and this is what I'm doing. I will probably keep going deep, even if the models become super great at PhD level intelligence.
Yeah, like for what it's worth, like at least the way I rationalize my work and performance is that like a lot of like we kind of know ML is going to be broadly useful, and now it's just a question of like making it insanely cheap so we can use it all the time and deploy it in different ways. And I suspect like robotics has sort of similar challenges as well. So like I think being good at performance will probably serve you well in robotics.
Yeah.
All right, so I see a question by Daniel. Like, yeah, it's regarding contributing to open source. Is this a good idea to learn?
I strongly believe so. So, okay, contributing to open source, I think it's something that you should learn to do, honestly. What does it mean? First of all, it's a good way to find a job, honestly. Like if you contribute to an open source project from a company or from a big project code base, it tells a lot about you. First of all, you can navigate a big, large code base. Secondly, you are productive from day zero. Like they don't even need to kind of onboard you. You are just productive. So it's a good way to learn and to actually enter the market. And I believe it's the best way. And I think TinyGrad is doing it. Like you just contribute to the code base and they hire you if you solve enough challenges. But on the other hand, I think you don't have to start by contributing to open source project if you have never done big projects by yourself. So start by doing a big project by yourself. You will build the confidence that is necessary to jump into a big open source project. And you don't need much to actually jump into a big open source project. Start by doing the basic things, like just fix their documentation. Start engaging with the people. Start getting noticed by them. They will give you a small task, like they will say, "Hey, I saw you working. Why don't you solve this issue? It's just a few comments that you need to clear," and then you do it.
Yeah, like for what it's worth, a lot of open source developers like just are overloaded with work, and they talk about their problems in public, whether it's on Discords like ourselves or like on their GitHub repos. So just be helpful, really, is
Yeah.
the sort of tip in the beginning. Okay, I think I see two more questions. So I'm not sure I follow what DSA is, but this is a question from Mohammed Silva. What's the significance of DSA
I think it's
for
for data structure and algorithm, right?
Oh, I see.
What is the significance?
Yeah, I googled this. I think it's data structures, but yeah, maybe we should answer that question then.
Yeah, I think, okay. So I think the question is mostly about should I do lead code to get a job in machine learning?
Or CUDA.
Okay, yeah,
Or CUDA.
because I get it
It's
a lot.
both or neither. It's both or neither.
So okay, okay. This is actually relevant because I believe it comes down to how confident you are with your programming journey. Honestly, I felt a little not confident with my programming skills without doing lead code. So I actually did lead code also just to improve my confidence, not because it's necessary for you to like be a master, just for my own self-satisfaction. And also I like to kind of having better problem solving skills. So in the year I quit my job, and every morning I did at least one lead code problem, mostly for just self-satisfaction and self-confidence.
All right, I think we'll take two more questions. And then folks, if you have more questions, again, Umar is very active on Twitter, on his Discord, so you can like reach him there. So yeah, it's another should I study X or Y question. Should I study AI infra, Triton, CUDA, and VLM, or AI algorithms, efficient transformers, and
I
variants?
think I can go deeper here. Oh, okay. I believe if what is happening right now, people think that either I learn high-level things or I learn like low-level things. I think the market right now is in such a position in which a lot of people are actually familiar with the transformer and the deep learning architectures in general, much more than like last year or 2 years before. So it's required in the market for you to know a little bit more about what happens under the hood. Because the material before was less accessible, there was very few tutorials, very few books, very few stuff around. Right now there is a lot of stuff around, so it's expected for people to know a little bit at least about low-level stuff. So you should at least know what is Triton. You should at least know how VLLM is working, what is page attention. Maybe you don't know how to derive it by hand, and that doesn't matter, but at least you know all these topics. So don't always think in terms of X or Y. It's about I need to know also a little bit of Y because it's relevant right now in the market. Otherwise, you have too high level overview of what is deep learning. Before you could be excused because the talent was there was such a shortage of talent that knew these things that everybody closed an eye on low-level things. Right now, there is no such a talent shortage, especially on these high-level concepts. So you need to go a little bit low-level to at least be more competitive on the market.
All right, maybe I lied. We'll take two more questions because one is very short, which is going to be the last one. Where in the stack do you think there's opportunities to optimize chips, hardware, CUDA, the architecture?
I think it's the software stack. I believe it's like there is a lot of job in the software stack to be done. The hardware is there. Just look at the a lot of labs actually they use, for example, even in production, software, like a generic software that is not optimized for the hardware. Because again, the problem was a lack of talent to optimize it, and secondly, the market changes so fast that you don't want to commit long term on optimizing something that may not be necessary for the future. So I think right now we are in a point in which we have a lot of first of all, we settle down on the transformer model. Everyone is using the transformer for everything. So there is a lot of things that we can do because things will not change so much from the architecture level. So that's why we are optimizing the kernels, the stack on top of it, the inference stack, the KV cache, distribution, context modeling, etc. I saw the question from Phil Butler about 10 hours. Yes, Phil, I am super, super, super fan of the 10,000 hours. I believe it's the only rule that matters in life. It doesn't matter it doesn't really matter where you start. It doesn't really matter which roadmap you have. It doesn't really matter where you live. It doesn't really matter what skin color you have. Just put in the 10,000 hours, and the fastest you do, the better. Sometimes you cannot do it faster because, as I said, for learning Chinese, you cannot fake it. You cannot do it fast. You just need to put them 10,000 hours distributed over 5 years if you want to master it. But for some things like machine learning, especially programming, you can accelerate your learning pace by leveraging the modern tools. And that's why I quit my job, because I wanted to do it fast. So otherwise, I could just do it at night and spend 10 years doing it.
All right, I guess maybe now it's good time for our last question, which is, what's your AGI timeline?
So depends on what you mean by AGI. It has been achieved and has not been achieved yet at the same time. That's what I would like to answer on this one.
All right. Well, I still see more questions in chat, but I suspect we could probably keep going for a long time. So folks, if you have more questions to Umar, please feel free to tag him on our Discord. You can go to his Discord as well. It's also very helpful. Join people in the 100-day CUDA challenge. And
so
Umar,
I'm a little hard on people, right? When on the CUDA challenge, and also on the on the Twitter, every time people ask me for a road, I'm very hard. Like, there is no roadmap. Like, I know it can be discouraging for some people. Honestly, I try to be as truthful as possible. Like, I'm hard because I tell you the truth right away. I don't want to like sell you a course, or I don't want to sell you anything. I just try to help you here. So yeah, thank you for joining this talk, and thank you, Mark, for hosting. Thank you, Phil Butler, also for like arranging all this. Thank you all the GPU mode sponsors and audience and the Discord guys, and thank you, deep learning gods, for guiding us.
Thank you. Thank you, Umar. This is fantastic. Thank you so much, everyone, and see everyone next week. Bye-bye.
Bye-bye.